Your next architecture decision isn't blockchain or database. It's deciding where trust must be cryptographic and where conventional infrastructure is enough. In this module, we'll design hybrid systems that keep strong, verifiable guarantees without sacrificing performance, cost, or operational sanity. Modern trust architectures are pulled between two extremes. Traditional enterprise systems are fast, flexible, and private, but they're easy to tamper with, easy to spoof using AI, and ultimately depend on administrators you simply have to trust. Pure on-chain designs flip that. They give you strong, independently verifiable history, but with higher latency, full public visibility, and significant operational cost. The real design challenge in this course is deciding what absolutely must be verifiable, and pinning only that to stronger, more rigid trust anchors. Designing for verifiable trust means constantly trading off assurance against cost and latency. Pure off-chain systems are cheap and fast, but trust rests heavily on organizations and their internal logs. Pure on-chain systems maximize immutability and transparency, but every write is expensive, slower, and often public. Most real architectures land in a hybrid middle. You keep existing systems, then cryptographically anchor what truly matters on-chain using commitments, verifiable credentials, or ZK rollups. We're layering trust, not rebuilding everything. Here's the mental filter you'll reuse in every design decision. If corrupting a record would cause a catastrophic loss of trust, that record probably belongs on-chain. That usually means 4 classes of data. First, rights and ownership. Who controls which asset or entitlement? Second, agreements and commitments. The rules everyone is assumed to follow. Third, evidence and logs. The records you'll depend on in a dispute. And fourth, core security boundaries. Keys, roles, and governance decisions that define who can change what. In real systems, most data never touches a blockchain. Heavy media, AI datasets, and model weights stay in object stores. Personally identifiable and regulated data usually lives in hardened, compliant databases. High-frequency telemetry is handled by streaming and analytics pipelines. And core business logic, UI state, caching, and search run on conventional services, with only key integrity checkpoints anchored on-chain. In pattern A, the blockchain is the one authoritative source of truth for core state, balances, ownership, and critical policy. Everything else, like your SQL database, is effectively a cached read model that can be rebuilt or corrected from the chain. The golden rule is simple. If the database disagrees with the blockchain, the database is wrong. This approach fits high-stakes domains, financial settlement, NFTs or token ownership, and critical policy decisions where disputes must be resolved by on-chain history. Pattern B takes the opposite stance. Your existing systems remain the operational source of truth, and the blockchain becomes a tamper-evident log. You periodically hash critical records or events, and anchor only those hashes on-chain. Later, you can prove that a specific ERP state or document existed, unchanged, at a given time, without exposing any sensitive or personal data. This fits supply chain provenance, audit trails, and dispute resolution scenarios where you need strong evidence, not full on-chain data. Identity and access management is the glue between people and cryptographic keys. An employee never talks to the blockchain directly. They authenticate through SSO, which asserts who they are and what they're allowed to do. That identity is mapped to a specific key in the key management system, which is what actually signs a transaction. The critical risk is key binding. Can you later prove which human, role, or service actually caused that signature? Strong auditing and clear mapping live exactly here. In most implementations, you don't ship all your data to a blockchain. You keep the database where it is and anchor it by committing only a cryptographic fingerprint. Take your off-chain records, structure them into a Merkle tree, and publish just the root hash on-chain. That tiny value is your tamper evidence anchor. Later, an auditor can recompute the Merkle root from a subset of records and compare it to the on-chain hash. If they match, integrity holds. If not, something changed. Think of this integration flow as the nervous system that connects blockchain to the rest of your stack. The node produces raw signals, new blocks, events, and transactions. An indexer or listener turns those into structured, domain-specific events. A message bus like Kafka fans them out in real time to enterprise systems. From a trust perspective, the key requirement here is idempotency. Consumers must safely handle duplicates and replays, so an attacker can't trigger the same economic or business action twice. Security and risk monitoring for blockchain systems means treating on-chain activity as just another critical telemetry source. Your SIM or monitoring stack should ingest node logs, smart contract events, and off-chain application logs, then correlate them in real time. The goal isn't only alerts on attacks, but also compliance evidence, anomaly detection, and clear forensic trails when something goes wrong. Zero-knowledge proofs let you prove that a computation was done correctly without exposing inputs, model weights, or business logic. You can treat your AI system as a black box. Data goes in, results come out, but only a compact proof is shared. Verifiers can cryptographically check the proof on-chain, gaining strong trust in the outcome while you keep algorithms and proprietary data completely private. Use this checklist as a practical gate before funding any trust initiative. First, define trust goals. Is the primary outcome stronger integrity guarantees, better auditability, or both and? For which stakeholders? Next, select the architectural pattern. Blockchain as source of truth, or append-only log that shadows existing systems. Then design integration with IAM, SIEM, and key management. Finally, test auditability in practice. Can an independent third party verify your claims from the evidence alone? As you design verifiable trust architectures, keep one principle front and center. Maximize integrity, minimize complexity. Use cryptography, blockchains, and ZK proofs only where they materially improve assurance. Favor simple, well-audited components, clear trust boundaries, and explicit assumptions. That balance is what turns integrity from a cost center into a competitive advantage.